Assalamualaikum to our dearest Dr. Ujila. Today we are going to present about engineering application of thermodynamics. We have chosen heat pump as our engineering application. So our group consists of 3 members. The first one is me, Muhammad Idzlan bin Azmi, metric number 212655. Next one is Ahmad Danish Syafwan bin Azeiz Badlei Syah, 210060. And the third one is Muhammad Azrul Hisyam bin Azmi, 213222. So today we're going to talk about description of heat pumps, the types, the fundamental principle of first and second law of thermodynamics, and thermodynamics analysis. So Azrul, you may have the spotlight.
All right, thank you, Idzlan. Okay, a heat pump is a device that uses a small amount of energy to move heat from one location to another. Heat pumps can be used for both heating and cooling and are often more energy efficient than traditional heating and cooling system. In heating mode, it works by extracting heat from the air or ground outside a building and transferring it indoors to heat the interior space. In cooling mode, it does the reverse, extracting heat from the interior of the building and releasing it outside. Okay, next slide, please. All right, this is the types of heat pump. First is water source, second is geothermal or ground source, third is air source, and the next is solar assistant, next is exhaust air, and last one is absorption. Okay, next. All right. I'm gonna talk about the principle of first law of thermodynamics of heat pumps. Next slide, please. The first law of thermodynamics, are also known as the law of conservation of energy, states that energy cannot be created or destroyed, only converted from one form to another. In the case of a heat pump, state the increase in internal energy of a system is equal to the thermal energy added plus the work done on the system. The first law of thermodynamics states that the energy transferred as heat to the hot destination is equal to the energy put into the heat pump as mechanical energy minus any losses due to inefficiencies in the system. This means that the efficiency of a heat pump can be determined by the ratio of the energy transferred as heat to the energy input as mechanical energy. Okay, let's see the example in the slide. In the operation of a commercial heat pump, the energy transferred to the inside of the building QH was found to be 80 kilojoule, whereas the thermal energy extracted from the cold outside air was 60 kilojoule. To achieve this, the amount of electrical work W needed from a compressor was found to be 20 kilojoule. All right, as we can see, these figures are in accordance with the first law of thermodynamics. Using the symbol from the diagram, this reduces to QH equal to QC plus W. Then we try to plug in 80 kilojoule as a QH equal to 60 kilojoule as a QC plus 20 kilojoule as a W. What this shows is that 60 kilojoule of free energy from the cold outside air is being delivered to the inside air for every 20 kilojoule from the heat pump. Okay, I'm done for the fundamental of first law. Next, Idzlan, can you talk or discuss about the second law?
Thank you, Azrul. So continue on principle of second law of thermodynamics on heat pumps. So the second law of the fundamental principle of second law of thermodynamics of heat pumps, where energy has quality as well as quantity. The second law of thermodynamics states that heat will flow from a higher temperature region to a lower temperature region unless other measures are taken to prevent it. So second law of thermodynamics, which can be understood with the schematic diagram. Here you have a somewhat device working as two-dimensional level. So we can assume TH is higher than TC. But what is the unique thing in this? The unique thing is what a pump does. If you talk about, for example, a water pump will pick up water from a lower level and we discharge it to the higher level. So this is doing somewhat similar. Looking at number one, so it does picking up heat from a lower temperature source, that absorbing heat which is Q in, and it will rejecting heat which is Q out. So this is the opposite heat flow, where against the second law of thermodynamics, this is not possible naturally. We're talking about the natural flow of heat from highest to lowest. So you cannot have the reverse flow of heat without any work input. So looking at number two, so to maintain this, we need to provide some energy input. in form of work. To understand it clearly, to run a water pump, we need to provide some electrical energy to, for example, a motor, where provide work input that will picks up water from lower level to high level. Okay, so it's similar happening to heat pump. You put in some work energy in terms of electricity, where it picks up heat from the lower temperature source and throws it at the high temperature source. So basically, this is the concept of heat pumps of second law of thermodynamics. So continue with Danish.
Okay, now let's take a look at the thermodynamic analysis of heat pumps. So to analyze the heat pumps, we will look to the four things, which is the coefficient of performance, COP, Carnot cycle, refrigeration cycle, and entropy. Okay, so for the first one is the COP, or coefficient of performance. Coefficient of performance is a measure of the efficiency of a heat pumps. The COP for the heat pumps we can obtain by calculate it by using the equation, the desired output over the required input, or we can simplify it as QH over work net A, or we can also use as QH over QH minus QL. Then for the second part is Carnot cycle. Carnot cycle is crucial since the COP of a heat pump is limited by the Carnot efficiency. So the equation for the Carnot cycle COP is 1 over 1 minus TL over TH. So by obtaining those both two COP, which is the COP of the heat pumps and the Carnot cycle COP, we can determine either the heat pumps is irreversible, reversible, or impossible heat pumps. Next, we look at the refrigeration cycle and entropy at the next slide. There are four main processes that we can obtain here, which is the evaporation, refrigerant, expansion, and condension, as well as compression. So by looking at these four processes, which is compression, condensation, expansion, and evaporation, we can obtain the energy destructed or destroyed in those processes. And by using the energy destructed, we can obtain the efficiency of those four processes. These processes, this efficiency is crucial because it can manipulate the coefficient of performance of for our heat pumps. As an example, the higher the efficiency of compressor or the efficiency of the refrigerant, it will increase the coefficient of performance of a heat pump. While if entropy is generated during the compression and expansion processes, it will reduce the efficiency of the heat pumps. So to conclude the discussion today, we can summarize that a heat pump is a device that transfers heat from one location to another location by using a small amount of energy. The performance of a heat pump can be analyzed using thermodynamics, particularly the concept of the coefficient of performance, Carnot cycles, refrigeration cycle, and entropy. The analysis can be used to optimize the efficiency and the effectiveness of a heat pump. So that's all from our discussion today. Thank you, Dr. Ujila, and thank you all.
Thank you, Dr.
Thank you.